Ma'am, you are not audible.
Okay, so hello everyone. Yeah, I said we'll start by 6:10, but I guess we'll see as people join and we can start ahead. So, we're already at week 10, and followed by it, we'll only have, let's say, two sessions exactly, and one more extra session. If you have any doubts or something, you can post in discussion forum, or you can let the NPTEL people know. So accordingly, we'll do the extra session if it's needed, then only. Okay, and followed by that, you have your exams for ahead. So, last time we saw something about the sensitivity specificity, how to do this region of convergence analysis, receiver operator characteristics, not region of convergence, but receiver operator characteristics, where we saw sensitivity specificity, how to see if our data has been correctly classified and if it's being presenting appropriately or not. So followed by it, we also saw this confusion matrix. What this matrix was nothing but a table that we made based on the matrices. This was all nothing but it was similar to how we had previously made our alpha error, beta error, and following the true positives, false positives, true negatives, false negatives, and all. Okay, so it's the same thing again, but just two, three specifics that I want to tell you through the slides, which are important for you to know. I won't go through the entire lecture again, but it's just the crucial parts in it that I think that you should know if you haven't or haven't gone through the lecture, or you have also gone through the lecture. Still, you should pay attention to these three minor details. Okay, so till now you all might have known that how these fractions and so what's the formula for sensitivity, specificity, how do you make the curves for them, how we it's like as and when how we move our threshold, how our specificity increases and sensitivity drops. Okay, so these are other different examples for it. Now we also saw that when we have to do this analysis, what we indeed do is like after plotting the sensitivity versus 1 minus specificity, we compute the area under the curve. Now this area under the curve would be based on an analysis where if it's like, let's say this coordinate 1 comma 1, then you'll get a perfect 100% of value. That means that it's very perfect. You have got everything that you're betterly classifying in between both of them. If it's in between this line, you won't be able to say that you are able to classify or your classifier is correct or not. If it's below it, It's totally false. If it's above it, okay, can say till some point it can make, but it would also have some mistakes in it. Okay, so this is how you interpret the curves that you make. Again, here perfect means no false positives and no false negatives. It is like 100% true data, 100% true classified data. Okay, so hence they have given the same definitions that we also saw during the assignment, that how you call as a classifier a true, that it will have a true positive rate or the fraction and a low false positive. Bad is like low true positive and a higher one false positive. Some cases you also need a bad classifier where you also know that the data that you're trying to fit is not the actual data, but indeed you want to see that how well it's not been able to show you the true picture that you want to. So in such cases, you should also know if it's a bad classifier or not. Again, a line that is passing to 45-degree or to origin is also considered as a bad classifier. You can say if it's helping you to differentiate in between two structures or not, but that's a different set. That is something called as clusters. Here is like if you have two different things, but don't confuse it with this one, because here you're making you're doing some operator characteristics where you're taking the same data set and interpreting the same data set. You don't have two different data sets again. So normally people do those mistakes where they confuse ROC analysis with cluster analysis. So both of these things are two different parts. Okay. And then indeed you'll compute the area under the curve. It will be maximum when it would reach this particular value of 1, when the coordinates are like 1 and 1. Okay. Then all of it same. Then how do you correct or see for the threshold? Thresholding, you'll also get some techniques where you need to find the optimum threshold for the same. But those are like through tuning methods, and there are different Python functions also available for the same. So that's like, okay, you can go through them. Not that too in detail, but yeah, different type of techniques that are available there. So here they have just given an example, different variables. Probably they'll try plot it. Yeah. So these were the Python's function that I also wanted you to stress upon. That one was like data frame.describe. So in very of our earlier slides or sessions, we went through that. Okay, how do you, if you make a table, then it's like if you load a data set, after loading it, how do you see the structure of it? So you describe it. Then how do you get the number of unique points that you have in there? It's like by a unique. And then how do you get the number of, it's like the count value of those unique points by the value counts. And then this ravel or ravel, whatever you call it as, it will return your one-dimensional array with all the input elements that you have given through the above three functions. So these functions are something you should know, because something like this might probably be asked during your exams. That okay, if this function gives you what and what's the description for this particular function. Later, they are just doing different tests they're finding, and then they'll do that logistic regression, or they'll do this. Yeah, they are doing logistic regression here. They'll follow the logic model. And finally, they are shaping, reshaping it, and yeah, here they made a summary table. We'll check for the sensitivity, specificity for it. They'll make a confusion matrix. So it's fine. Now from this confusion matrix also, there's another score that is called as F score, F1 score. So these are different parameters that you get from this metric. What is important for you is nothing but the sensitivity and specificity for now, that you should mostly stress on. So here you get the precision, you get recall. So we have already looked at precision and recall. F1 score and support is not that actually important, but yeah, precision and recall is what you can focus on till now. Now here are the formulas again the same. We already looked at the formulas during the last time assignments. Okay. So these were the points that I wanted you, that remember the definitions, what each function is serving you as, not more than that in it. Again, what is called as a good and bad classifier, those things. If you change your threshold, what happens? Okay. Now, till now, what we saw was different types of tests to check your independence value, to check your significance value. Now, there's something called a chi-square test. You all might have done it, the chi-square test during your class 10th, 11th, 12th. T-test, chi-square, everything was there during our 10, 11, 12, but we didn't knew about it. Again, during our bachelor's also, we'll have these things in our numerical maths. If not, it's like I had it after me, the curriculum changed, my batch. So then the new batch ones, they don't have numerical analysis anymore. So then they have to take an additional course of statistics when they do their PG studies. So for me, I already had these, but during that time, I was not so well aware about this technique. So for me, it was like, okay, only formula, do the solve the exams, you're done with it. But these tests are like, they'll revolve around. Each and every test are nothing but similar to another. Once you're well aware with the Z and T test, you can solve any particular test that will come to you. So previously, we saw there were different types of data methods. Okay. So I'll just take one different page. However, the instruction has written there, but we'll just take the extra page over here. Let's just take the page at the end. Okay, so we saw there were different types of data. It's like data was categorical, data was continuous, all those different methods. But now, if your data is nominal and if your data is ordinal, that is to be arranged in some orders. If your data lies in this fashion, what you have to do is like you'll have to do this chi-square test. Now, we have seen that, okay, one will do the Z test, one will do the T test. Wait. Now, this can be for one sample, right? It can be for two samples. Okay. It can be for a single sample, can be for two sample. And for them, we saw our different methods. We had null hypothesis, we had alternative hypothesis based on the sample mean, based on the population mean, right? When we had more than two samples, what did we do? Or more than two groups, or let's say samples. So which particular methods do we use there? Anyone? Yes, okay. Someone was saying something? That's a mic glitch.
Ma'am, repeat the question, please.
Oh, yeah. So when we had one sample, when we had to check for significance or differences for a single sample or for two sample, we always did this T test and Z test based on the sample size that we had. When there were more than two samples or more than two groups, what type of test did we do there? Did we do Z and T test or some other type of test?
Chi-square test we are using.
No, very basic. Go back to very basic. When we were doing T test and Z test, when we had more than two groups or samples, we were doing something as analysis of.
ANOVA analysis.
Yeah, yes. Thank you. So we were doing this ANOVA there. It's like analysis of variance of our samples. So we were checking, and
Yes,
followed
ma'am.
by ANOVA, we were also doing something as F test, which also gave us the it's like analysis where our variances were equal or not. First we'll do this F test, then we'll do this ANOVA, then we'll check, okay, if our samples are not. What ANOVA basically was, it is nothing but multiple or simultaneous Z or T test. So it would be followed based on the sample size. You will, it's like get if you are doing Z or T. Basically, when you are whenever you're doing for research, your sample size is very restricted enough. So it would be a T test. But you are doing something as CAC based test, you'll have generated data. So there your sample size might be more than 30 samples. So there, in that cases, you can do this Z test. Now we also did so this ANOVA or this F test. These kind of testers are nothing but these are generalized tests. Wait, what happened? Yeah, so this type of tests are nothing but generalized. So if you have also, so even after for one sample, if you get it for two sample, you can still do ANOVA. You don't need more than two samples to do because it's nothing but simultaneous or multiple T tests or Z tests that are being done over there. Now we also had something as proportion test. We checked in between population proportion. EX cap or something like this. So we were checking for population proportion test, if it's similar or not. What proportion were like nothing but ratios of a population within the single data set. So these were also for a single data set for two data sets. Now if in this case, if it's for multiple, Then we do something as chi-square test. Okay, so this was how we came upon for this chi-square test. Now chi-square test is also a generalized form for it, but this is a very qualitative test which will tell you two things. This is there in the slides, but better if we make this flow chart previously. First is about the independence of variables. And second is the goodness of fit. Goodness of fit matrix, if you all might have remembered, we had R square, we had RMSE and all. Now chi-square will also tell you about the distribution of your data set using the again summary tables that we made, the OLS summary tables, least squares formula. So it will also follow the same method, but it's just for the population proportion. So this was how the total motivation for it. When you do chi-square test, you make something called as contingency tables. These tables are similar, not similar to how you do your confusion metrics, but you it's like, and they have some resemblance there. So we'll look how we go through them. Okay. So here was the agenda that first we'll do it for independence. Same thing is written over here, if you understand. Okay. So yeah, so what we need to check over here in chi-square test is nothing but if any two variables that you have, if those variables are independent or not. So in a way, you are checking if population variables that you are checking within and the frequencies, how many times that particular variable has occurred, if they are independent or not. Again, it is qualitative and it follows for nominal data. It's not for your continuous data and all. Okay. So there's this example. In this example, there are two research questions that they are asking over here. This is your first question, Q1. This is your second question. So now they want to check if there's any relation in between these two questions. If I say that if a person who is residing in this northeast region and has this financial achievement as like, investment as stocks to be made, is there some dependence in between these two variables or not? So for the same, we'll make this contingency table. It's similar to how you do matrix multiplication or diagonal multiplication. So we'll make the matrix matrix like this stands for northeast, this stands for this midwest, this stands for south, this stands for D stands for west. So all the variables by their name. E stands for stocks, bonds, and G. So this is your question number 2, and this is your question number 1 right here. So here you'll be checking how independent one of the variable is with the another variable. So how many times that particular variable has occurred is the frequency that you'll have over here. With respect to the frequency, now since we are checking for the population proportion and chi-square test is valid there, we'll also get a probability for that particular frequency. How do you get those? Now for getting the frequency, you'll have to account for the total number of counts in that particular data set. So that you'll get by summing up the entire amount. So for A, your entire thing would be summed up here. For B, entire thing would be summed up till here. C summed up all the columns in C, D and D. Again, if you do for E, it would be column wise for E, F, G. Okay. And for the entire data set would be N right over here. So it can be the sum of this all and sum of this all. You multiply both of them. Okay. So same thing. Now, if we saw that there were two things possible, one was mutually exclusive, another was independent events. Here we want to check for independent events. If they were mutually exclusive events, it would have been 0. Now, if they are independent over here, so their intersection will give us rise to two independent multiplications of both of them. Now, if I need to find the probability of one, it would be events that are occurred in A being divided by the total number of counts there. Similarly, for F, I'll do intersection, I'll get it. But now if I want to find the frequency, in terms of frequency, what's the probability of it? So it would be, I'll have to multiply it by the total number of counts that have occurred in the total data set. Okay. So this EAF would be nothing but this A, this F right over here, this AF, this is your capital F, total number of count. NA is nothing but how many times this occurred. NF is nothing but how many times this occurred. So you get the variables from here. When you input all the data over here, you'll be able to compute it. Now, this is not that numerically extensive or something, but if you go ahead, here's the formula for independence. So what we did is nothing but your Ni is like the row wise, then you have column wise divided by the total of all the frequencies that you have. Simple formula for computing the expected frequency. Now you want to compute it for the independence, for the chi-square. So what it would be? The observed frequency minus the estimated frequency divided by estimated frequency. So if the formula here stands confusing, So what it means is that this formula does not have the denominator as squared. Okay. So it is nothing but F naught minus Fe whole square divided by Fe. Summation row wise, summation column wise. Okay, that's it. This is how your chi-square test would be along. Wait, if I have something written. Yeah. And here, your degree of freedom would be based on two variables. One is your row variable, another would be your column variable. So it's nothing but row minus 1 times column minus 1. So it would account for the factors that would be affected by the rows, also by the columns. Okay. We'll take one example. We want to see if there are two variables like gasoline and income, if both of them, these variables are dependent on each other or not. Okay. So, 2 minutes. Yeah. So here what we have is this. Okay. So we have this 4 categories right here. So this is our Q1 again. This is our Q2 again. So for Q2 we have 3. This Q1 we have 4. So what would be our degree of freedom over here? We just saw the formula now.
6. It will be 6.
Yeah, yes. So this is nothing but 2 times
1 and 3 minus 1.
Yeah, yes. So this is our degree of freedom over here. Now we'll have some values that would be inputted into it. From those values, you'll be able to compute. So chi-square, this type of distribution is the right skewed, and that to be upper hand skewed data set. So if you see this data, it's like the curve the instructor has drawn, it's like right skewed and it's towards the upper hand. Now, if we are taking the alpha value as 1% significance or 99% significance, through the table or through Python, you'll get the probability that it has at that particular critical value. So this value is already available to you. So then you'll start making your hypothesis from the same. So if your value is greater than this particular value, you'll reject the null hypothesis. If it's less than it, you won't reject, or you will accept your alternative hypothesis like that. You'll accept your null hypothesis. You won't reject it. Yeah. Yes. So how can you, it's like here, if it was 1%, you get the value from the table. If it's not, if you want to do using Python, so Python follows the other way around. In the table, you'll have to look at for 0.1 value. In Python, you'll have to write for 0.99. So that says like for 1%, it would be 0.99. You get the value for it. Both values are similar. So it's also 16.812. Here you also have 16.811. Okay. Now you make entire table out of it. Now for this particular header, regular, this is your sum here. So that 238 is the sum of all these variables here. For this particular header, premium, this is your total sum. That is sum of all these variables. Similar for extra premium. For less than $30,000, you have here sum of this all terms. So that is your this for N1. Then this is for N2, N3, N4. Now sum you all of them here, sum all of them here. What you get is 385 right here. Okay. So this is how you check for, it's like how many number of variables or what's the frequency of all of your counts that you have in. Now, if you want to compute for frequencies, you do for again. So if you want to find it for, let's say this value, you'll have 85 over here. If you want to find for regular and that to be for $30,000, what you'll do, you'll have this particular variable times this variable divided by 385. Okay, so you have 107 times 238 divided by 385. So you compute it for all variables accordingly. And then this observed frequency, expected frequency, expected frequency. What's your expected frequency? Was the value that you already get. Observed frequency was the value that we had over here previously. That was given to us. Okay. So from there, you will also get something you'll reject. But same thing you can also do using Python. If you want to cross clarify it, that's like, yeah, there's another example for the same. For Python, they have given or not. Let's see. For two proportions. Yeah, so it's the same. So you do on make tables, make tables, make tables. For this, you'll have to recall all your knowledge for this population proportion. How do you compute the mean for that population proportion if those parameters are not given? And let's say they want you to do exactly from scratch. So you have two different populations given. Now you have to compute the mean for that population. After mean of the population, you'll compute the frequency counts for it. Then you'll come up to a point that you'll do the chi-square test. Okay. You'll have to go back to, I guess, week 4 and week 5. And from there, you'll have to cross check your population proportions again, and then you can jump up to these points. I guess here they don't have, probably in the next ones they might. Let's see. Yeah, there's Python here. So there are two codes, there's example, yeah. So here they have read a CSV file. After reading the CSV file, our hypothesis was if there are these two variables, if the variables are independent or not. Okay, so they made a table for only those two variables where one is your row, another is your column. Okay, so looking at here, what the code suggests is this G variable, probably your grades, is your row. SM, I don't know what this SM is, student motivation. Oh, sorry, this is gender and this is student motivation is your column. Okay. So then you make the table like this. So here they have just written the table in presentation for your sake of understanding. So if you see, if it's 0, you get a male. If it's 1, that's a female. Your student motivation has been also graded. So this is all ordinal data that you have over here. And then they have summed up. So these are all your frequency counts. So you have 14, 22, 14, you have 29, 21, 50. And the final sum would be here for all of them, right? Because you only had this two variables. So here this is 2. 1, 2, 3. This is 3. So here your degree of freedom would be 1 times 2, that is 2. So then you compute this things again. Then you find for chi-square, compute the value, see if they are dependent or not. So if you want to do everything using Python, directly import this chi-square contingency. Using chi-square contingency, if you directly give all of the observed values that you have computed. So it's much easier to compute the observed value than to do your frequency measurements, right? So then you write in those observed values over here, put in the data in there, you'll get the probability. Probability is 0.3, degree of freedom is 2. Then what happened? Yeah, degree of freedom is again 2. You show the output, the table of it. So this is your frequency table or the contingency table that you make. So all the values would be similar if you cross check from that particular analysis, and then you compare for the chi-square goodness. Oh, sorry. Yeah, then what we'll do, you'll compare it with the initial value for 0.1 that you have, and you'll see if they are independent or not. That's it then. So if you don't want to compute it for frequencies, you can directly assume this particular function. So remembering this function is an important task over here. Remembering the frequencies is not, because now you know, seeing the table, you know directly. So that will come out of intuition that, okay, I have this many counts of frequencies over here. This is the total. This is the total. What would be the probability of it? You can directly write the probability there. Now for frequency counts would also be out of intuition only, where you have the observed values, you have the expected value, you take the difference out of both of them divided by your estimated value that you already had. That is your chi-square value. Compare both of them. But while comparing, now you don't know the chi-square value for that particular significance that you have already set it at. So for that, you'll need the chi-square table. For the chi-square table, you'll have to see. Now let's say you don't have the chi-square table with you, or you don't know how to read that chi-square table. What you do, you go in Python, write the probability mass function for that, PPF, you'll get the particular chi-square function for it. You only need two parameters there. One parameter would be your degree of freedom. Another parameter would be your the level of significance that you want to test in. That value, you know, you have the frequency table, compare both of them, you'll be able to see if your variables are independent or not. Apart from independence, you also have something as goodness of fit. Okay. So that was all about independence. If one has any doubt, you can let me know, because after that we only have goodness of fit and some little part about clustering, then we'll be done with the session. So any doubts for the first half? Any doubts?
No, ma'am.
So, next part is the goodness of fit test. Okay. So for goodness of fit, what do we see? We'll see if our data that we have and the data that we're trying to predict or estimate, if our estimated data is fitting well with the data that we have truly. So if it's a good fit or a good representation of our presented data or of our observed data. Okay, so that is how what your goodness of fit tells you. Another goodness of fit parameters that we have seen till now was R square. Another was RMSE. All those parameters we have seen. We also saw something as adjacent R square. So if one value increases, another decreases. If degree of freedom increases, another one will also increase and decrease. All those parameters we also saw. Okay. So for goodness of fit test, this one, your degree of freedom will change. So any instincts from someone that why will our degree of freedom change over here? Why does it matter here? Because if you see the formula here, one tells you the number of categories, another tells you the number of parameters. So why are these two things important when you're trying to fit a distribution and you're trying to say if your distribution is correctly representing your data or not? So that these things will help you remember the formula much more easily instead mugging it up like that. So let's say if I want to fit my, if I have some data set, let's say my data set is something like this. I think, okay, it's something similar to normal or Gaussian distribution. I might try fitting it to that. Oh, sorry. Try fitting it to normal or Gaussian distribution. I'll have to see if it's fitting well or not. So for the same, I'll have it's like normal and Gaussian distribution have their own parameters. One might have mu, one might have standard deviation. Those parameters might also be similar or less than. It's like for a normal distribution, you don't have any. For Gaussian distribution, you don't have standard deviation. It's only mean. So you have another parameters over there. So when you're trying to fit your data with some another distribution, that distribution with its own parameters. Let's say you have Poisson's distribution. So for Poisson's distribution, you have a lambda parameter that is similar to your mean. So we need to account for the number of parameters that we are going to try to extract from that particular distribution model in order to say that my data is being fitted by this distribution with the goodness of fit as this much percentage with the parameters, model parameters as so and so. So these parameters are the one are those unique values that are presenting my data set and might also help me classify or differentiate if I had any two further classes, something like that. So for that particular case, one, your number of categories. So how many groups you are is like doing your measurements through. So let's say if you have two groups, it would be two here. And then P is nothing but how many parameters you have into your distribution that you're trying to fit it to your data. So same in this cases. And then you'll subtract it from one, same way that if you change the last element, your data mean would alter or not alter. Okay. So that is how the motivation behind degree of freedom for this, not as R minus 1 and C minus 1, but it is directly K minus 1 minus P. So it's goodness of fit. So you're trying to fit it using something. So always remember fitting would be some, with respect to some distribution. That distribution will have its own data parameters. Those parameters you consider how many parameters minus 1 and you have number of categories minus 1. Okay. So then it's like they make the, so here they are checking it for Poisson's distribution. So checking if your data has this Poisson's probability distribution or if it does not have. So again over here, if you might also have noticed for null hypothesis, we never give it to equals, or sorry, for alternative hypothesis, it's never equal to. So null hypothesis has been given that it is a Poisson's distribution, whereas alternative says it does not. Okay. So then we'll compute the mean of the samples. We have the frequency of the samples. We'll compute the expected frequency as nothing but the probability of your samples. So same formula that you had previously, chi-square, again same thing. So here you're dealing with Poisson's distribution. So Poisson's distribution, if you might have remembered, the formula was something like e raised to negative mu power x divided by x factorial, something like this. Okay, where your only variable is nothing but this mu, that is nothing but your data mean. So you have as k minus 1 minus your parameters are nothing but 1, so minus 1. So that is nothing but k minus 2 is your degree of freedom over here. Okay. Then this is your example. This is also example. So what you have over here is the number of arrivals with respect to the frequency counts that have already been given to you. So you write it into a direct table here. So they have fed it into Python. So you read the final metrics. You compute the total frequencies for all of them. Then you compute the mean for them because we know that there's only one variable over here. You compute the mean for them. Then you know if you want to find it or expected frequencies, you will have to multiply it using the n, that is total number of values that you got. So this would be 100 here, this would be 100. This is your all the values that you have. This is the frequency and this is the data variable that you have. Okay. So then you run it through all. compute the expected frequency. You now know the expected frequency here. They'll probably try to reshape it into some metrics. When you try and reshape it again, they've tried, now they made another table where one is your observed frequency, another is your expected frequency. Okay. When you have your observed and expected, it's much easier for you to compute the chi-square distribution. So then you take difference between all of them divided by the sum of the expected frequency. What you get over here is the p-value of 0.9. That means that, okay, we can reject the null hypothesis, can say that it is not representing something. Yeah. So it's rejecting the null hypothesis where we said that it is a Poisson's distribution. Well, it is not a Poisson's distribution no more. Okay. So something like that. Now, probably they're doing it for chi-square. So checking for the independence in between the two variables. So you get the chi-square for those two metrics. Now, can someone say why the degree of freedom? Okay, here it's only there. So our k number of categories were how many? Here. We have 9 or 10. 10 or more. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So total number of categories, what we have is nothing but 9. So we have 9 minus 1 minus 1. So this is nothing but 7. So 7 is your degree of freedom. Okay. Here you have 7. So be careful about the small terms. It's like people might ask you, okay, what's the degree of freedom here? What's the difference in between these two techniques and how you compute the degree of freedom if it's a chi-square test, if it's a z-test, if it's a normal mean test, if you're doing for t-test with sample size of something, if the standard deviation is known or not known. So you need, it's like, that's why mugging up won't help you in this cases. It's just your intuition that will help you. So for these also, it is, well, it's like, it comes directly if you try and understand the formula with it. Okay. So yeah, here again, it says that, okay, do not reject it. That's it. So another thing to tell you is nothing but you can directly compute it using Python if you have the variables with you in hand. If you do not have those, so here they checked it for independence, if the variable were independent or not. Up there, they checked it for the goodness of fit, if they were following Poisson's distribution or not. So there were two things that were going on here. Okay. 47 and then you have 49. Okay, that's clustering. Okay. So any doubts within chi-square for independence, chi-square for goodness of fit? So that's
No, ma'am.
Oh, okay. So then last thing we have is for clustered parameters. So clustering analysis, last time we had a question in assignment was something as, do we standardize our data before doing something or not? So there was some test or something. The test, it asked us that before doing that test, do we standardize our methods or not? Where we said that no, we do not, because for doing the standardized is like normality test, or let's say ANOVA, or let's say independence test, significance test, we never really manipulate our data, or we never really want our data to be unitless or measurementless, something like that, where we are not comparing in between data, but we want to see if any two variables or the sample size are like this or not. Well, let's say if you have two different groups, one group following a different pattern, another group following a different pattern, in those particular group, you might see a similar variance. So what I'm trying to say over here is, let's say if you have a particular model and you have, let's say one can be all blue, another can be, okay, one can be all this green values, another can be all your blue values that you have. Here, all your blue values. So what you see is nothing but here, based on the color, there's a difference in between the values that you're trying to see. So based on the green color, based on the blue color, you're able to see that, okay, there are differences. But in between these variables, there are not too much differences. So you see a similar pattern in between these variables. How they are being clustered, you see there are two different groups now that have been made. So one directly can recognize, okay, it's based on the color, I see a difference over there. But it's not, if it's not based on some colors, it can be something based on a dependent variable. Oh, sorry. It would be something that is based on an independent variable and a dependent variable. right? So let's say if this is your y and this is your x, so your independent variable versus your dependent variable. So those can be something based on those particular variables also. So now here we just want to see the cluster analysis and different types of data and how to handle them. Okay. So same thing, how do you see and how do you recognize how a child recognizes them? Then you also have learning methods, where in learning what you do is like, I won't throw high five words over here, but probably until now everyone might have heard this word. It's like you have something as unsupervised, you have something as supervised. So just a simple example, if one wants to buy something and I have given him all the guidance, advice or something, is like all set of instructions how to do those things. I've given him all labels to do. It's like I have told him that which particular path you need to go and how do you need to purchase. Would be something that is nothing but you have given a prior information to that person. So that is your supervised learning. Another is like if you don't have any information with you beforehand, but that data might be sensitive to some information that you also give it to you. So that is something called as unsupervised learning. Okay. So these type of learnings are also involved. So learning does not always mean that you have something and you're doing training and testing. So here learning is also involved to classify or to predict your data set. Okay. So here they have plotted it. You see two different distinct variations in this data set. So there are two different groups that are being followed over here. So for clustering, people usually do it for continuous data. They do it for interval based data, for categorical data, just to see a similarity or difference in between two groups. It's based on the pattern recognition. So how we do is nothing but we'll make the groups called as clusters. And to discover them is nothing but the aim of this cluster analysis. How do you differentiate them? How do you recognize both of them? Now here is the thing that comes, your standardization. I don't know if it's in between this lecture, but let's just write here for the sake of continuation. So what you do is standardization. Standardization, what it essentially is, don't say anywhere, but how do you do it is the procedure of, it's like it will help you, normalization. What it means is nothing but, let's say if 10 of us are trying to do something, and if we want to represent it for one person, that would be nothing but mean of all of us, that value person, a particular person will have that particular value, right? So that is nothing but normalized for all people. And you can say that, okay, that person is representing all 10 of us. So that value can be something which can be used for this. So that is nothing but standardization, where in a way you're trying to manipulate your data, but you're making it unitless. So it's no longer dependent on any one variable. It is measurementless. So what you tried and measured, you might have some bias into it, but that bias has now been accounted when you take it for all of the variables together. Okay. Now when you do this, what you end up doing is you'll have something, your values might be ranged in between a range of 0 to 1 if you normalize all of your data set. If you don't, and if you just take for let's say a subset of group or something, your data set would also be accordingly. So while doing standardization, what you remove is nothing but bias. So now you no longer have bias in your data set, and you would be able sorry. Yeah. So then you would be able to do this cluster analysis then. So how did we saw it was here. So we saw there were two different methods for the same. One was your supervised, another was your unsupervised, right? So cluster analysis is one part of this unsupervised learning. Another one is nothing but discriminant analysis, where you give some prior hand information to your data set. You tell it which particular group it has to group along, which object belongs to which group, and accordingly it will predict it. It's like it will extrapolate it on further values, and it will try and see if it's being able to differentiate or not. So that's your discriminant analysis. Whereas for cluster analysis, you don't require any prior knowledge, but as we said previously, to any specific information that you also give, it is very sensitive. So you're all clustering, the scores of clustering, how well are you able to differentiate in between two different data sets that we, I guess, previously also saw there were different clustering scores for them. So it's based on the distance in between the two variables that we count. So those would also matter there. Is like how far the matters are, how far the clusters are. It will also be biased based on that particular variable there. Whereas on the case of this discriminant analysis, it's everything dependent on the label that you're trying to give it to your data. If that label has been defined properly, if it has been classified previously or before, so it would be everything would be dependent on that something for the function that was built upon, but not the function that will be built on that is to be predicted. Okay, so there is only this two minor differences in between both of them. But for one who needs to do this unsupervised or supervised, according to the application, a person can decide. Okay. So same thing here, they have tried to classify here also. So here you have two objects. It's like one is your like, intermediate, and need. Sorry, three objects. You have three attributes for the same. You're trying to see if your objects and attribute would be differences or not. So then different types of data sets you can as like make as like you arrange your data set and you try and see how well you can plot it. So one such thing what you can just do is like, let's say if you have A set of data, B set of data, I guess we also did this previously. You directly do a scatter plot of it, right? And if you're here, what is if your goal is to see if there's a difference in between this A and B group after all of your analysis being done. Okay, so in cluster analysis, you don't need to do any independence test or goodness of fit test. Everything it's done over here. After this, there's nothing. So here, what you do is like, let's say if you have two different sets of data, that probably this variables you might have looked at that are this independent, are this related, are this dependent, something like that. So if you have tried and saw that, okay, and these two are, let's say, somehow independent of each other. Now, if they are independent, I want to see if these two groups are different or not. Okay, now, if they are independent, they should have been different. Now, how different are they? So then let's just make a scatter plot of them. How we saw previously that blue and green differences. If you get a plane of difference in between both of them, you can say that, okay, there's it's like differences in between both of them. Now, how well and using which method are you trying to do that will depend on this cluster analysis models that you have. So here they are again building up is like if it's for interval data, then if you have the data sets aligned, if you take mean of the data, if you arrange the data again properly, then the differences will also differ. Yes, Kanan, you have something to say? You're not audible. Are you trying to say something?
Test like F test and Z test, ma'am. For the
Exactly.
test value, will you give for in final exam? What is the value for alpha is equal to 0.01 and alpha is equal to 0.5? Will you
Yeah,
be
yes.
giving final exam?
Yeah, yes. The level of significance for which you need to test it, those values would be given in the exam.
And how many questions will be there in the final exam?
Can be 50, can be 100. So based on what the question paper is like. So I don't have information on it. Probably
Thank
100.
you, ma'am. Thank you, ma'am.
So then when
Ma'am, will
you,
they provide probability distribution table?
sorry,
Ma'am, will they provide a probability distribution table for checking P test values, T test, Z test?
these tables, if something that is needed, and if there's no Python availability there, the tables would be given to you. But when I gave the exam, for me, the values were written directly. Given that the probability for this and this value for this so and so degree of freedom is this. So you directly use that value over there. But be mindful while using also. So you should know what you're trying to do over there. Okay. So again, if they don't actually give the tables, I have not seen giving them tables, but what they give is nothing but the Python interpreter. So if you know there are simple functions. You have CMF, sorry, you have PMF, you have CDF, you have direct functions. Write the function against it a significance value and the degree of freedom, you'll get. But that is specific to a distribution that you're trying to check it on. So remember all those formulas is like you need to know the syntax for the same, directly add in those values, you'll get the probability instead of reading the table. So I feel that way comparatively more easier. Okay. So yes, Kanan, anything else?
Ma'am, in the assignments, there is no questions related to Python code. Will we get the Python code questions in the exam or problems and theoretical questions?
Well, in the previous assignments, there were questions related to Python. So we had to solve one assignment is what it was completely fully based on Python. So you had to solve it using Python. I don't know if you missed on that assignment or not, but yeah, yes. In the exam, there would be interpreters available to you. So some questions can be that, okay, if this is a syntax, how the output would likely be, or if this is output, how your syntax would be. There might be MCQs based on it, or there might be interpreters available to you.
And so there will be interpreter. If there is value, they will give what needed. Likewise, you are saying.
Yeah, yes.
Thank you, ma'am.
Okay. So here we have standardizing the data. So as we said, what we are trying to do is like we'll make our data independent of the measurement units that it was considered through, and we'll make it unitless. So it would be nothing but everything based on unitless variables. We'll compute the mean of the same. Finally, you'll also compute standard deviation here in -1 because of the degree of freedom for the same. And then you standardize all of your data. So here also, this is mean absolute deviation of your data set, absolute value of deviation that you're trying to check. So as one student said just now, is nothing but it is similar to how you do your z-score. So making it something similar to your z-score or constructing your z-score will help you make your data set independent of the unit that you measured it through. So this is nothing but your expected value that you're trying to measure, the mean divided by standard deviation. Everything would be unitless over here. You directly compute the z-score, compare it in between z-score. This z-score will also help you for outlier detection. What outlier is, if let's say I have some variables, some values of variables from 1 to 5. There are like 100 values. And let's say one value appears to be as 10. Now that 10 is nothing but my outlier, something that is not following the actual distribution of your data set, and it is very way apart from it. That number will also affect your mean of the distribution, your standard deviation of the distribution will include more and more variance to your data. So because of that particular data, you just directly do is like nothing but you remove that variable from your data set. While removing it, your data would make much more sense. So that is why people do something as outlier detection. Okay, you detect an outlier, you make your data more uniformly distributed, and then you do your analysis on your data set. So this is what is called as standardizing your data set. Okay, so again, you detect an outlier, compare it within. Okay, last is nothing but there are two methods using which you compute. It's like simple methods. How do you compute? So one such we saw that, okay, let's say there were two clusters, one using this, another using this. Within those clusters, let's say you have different points over here. Okay, something like this. Now, within this particular point, how do they make this cluster something like this? So they do it using by measuring the Euclidean distance. What is Euclidean distance? You all might have done using your classes. Let's say 11th and 12th, something is nothing but the distance in between two particular coordinates based on the hypothesis Python. So something based on the Pythagoras theorem. Okay. So there is one as Euclidean distance, another one is something as Manhattan distance. Okay. So I'll directly show you the example. So this is how you standardize your data set. Here, Euclidean distance, you compute the differences in between all the variables and you take a square root of them. So this is nothing but how you compute a Euclidean distance. This is like well much you all are well aware with this formula. Another formula for computing geometric distance is nothing but by the Manhattan distance. This is nothing but you take the absolute differences in between all the distances. So very basic, back to our preliminary 10, 11, 12th. So you directly compute the distances in between all the variables and you find the differences in between them. If you get some differences, it would be localized to the values, directly sum between both of them. Either it's your x coordinate or it's your y coordinate. So these two are nothing but majorly used methods for cluster analysis. So the method here that it follows for this one, for Euclidean distance, is the k-means. Okay, so what does this will do? This will compute the distance in between the centroid. what a centroid is nothing but a mean of a particular cluster. So that is nothing but by 3 number of values that you're checking. So this will compute the Euclidean distance in between the centroid of 2 different clusters or any n number of clusters that you're trying to classify. So this is nothing but based on this Euclidean distance method, this kind of technique. Another for Manhattan, I don't think so they have given. So there are just test of significances how you compute. There's also another this test that is nothing but combination or generalization of your Euclidean and Manhattan metric is nothing but Minkowski metric. So what this distance is, it will compress all of your values, right? So this is something form of a non-linear clustering method. So if one asks you, so what you do over here, you scale to a value of p for each of your differences, and finally you'll nothing but compress it to that particular value of p. So what that means is that you're trying to minimize your clustering parameters by the number of parameters you had in that particular distribution. Okay, it's a bit complicated to write or to implement it, but finally the values that you'll get won't be dependent on your data set. It would be way more generalized with respect to any technique that you try and use, either it's supervised or unsupervised learning. So if you want, you can, or going with the Euclidean and Manhattan also works most of the time. It will also give you much more accurate analysis with respect to others. Okay, so here they are comparing and they are looking at the matrix if it's symmetric or not, selecting variables, and I guess pretty much we are done with it. Any doubts in cluster analysis?
No, ma'am.
So if all of you don't have any doubts, we'll go ahead with the assignment task. I'll just wait for 2 minutes. If someone has any doubts, can let me know, and then we can go ahead with the assignments. Okay. Okay. So we have the assignment here for chi-square test and for cluster analysis. So all of the assignments, unsolved assignments, previous assignments are stored in the Google Drive. You can find the link of the Google Drive with a sheet that has been shared with you, and there all of the solved assignments would be there. I guess you won't need to find because after the session and probably a day after the session, you have your assignments for this week pending or due. So then everything would be revisited again for you and you won't need it. But if just in case while solving towards the end or while preparing for the exam you need, everything would be there available in the drive that is shared with you. Okay. So we'll start with the assignment then. So first question, sampling distribution for a goodness of fit of test is the what? Sampling
Normal
distribution.
distribution.
Sampling distribution for a goodness of fit test is the which distribution?
Chi-square.
Oh, yeah,
Chi-square.
yes.
Yeah,
So
chi-square distribution.
yes, so the type of data that we looked and how we are looking at based on the proportion, that is nothing but chi-square distribution. Okay, goodness of fit test is always conducted as, so we just saw. So how the goodness of fit was for which particular test and what that test was. Was it which tailed? Something like
Right skewed to us means upper tail.
yeah, yes, exactly. So null hypothesis for chi-square test of independence assumes that all the proportions are equal. Is it true or false? So null hypothesis and alternative hypothesis go just directly back to the equation. Will null hypothesis have an equal or alternative hypothesis have an equal? If they do, answer is true. If they do not, answer is false.
True, ma'am.
Exactly. So it is true. So just consider in mind that it's your null hypothesis. So yes, we assume that it is equal. Okay. So, yeah, yes. But then just don't go directly through it. Also look at what particular variable it is trying to talk for. Here our assignment is only for chi-square and cluster, so it makes sense. If it wasn't, then you'll have to look through the variable also. Okay. So statistical test conducted to determine whether to reject or not to reject a hypothesized probability distribution for a population is known as whether to reject or not a hypothesized probability distribution. Question is bit more
Goodness of
weird,
fit
but yeah, yes, goodness of fit test. Exactly. It would have been much nicely framed, but okay, yes, it's fine. So what's the minimum number of variables or features that one requires to perform clustering? Can we do clustering within 0 variables?
No, we can't.
minimum
So
two.
what's
Minimum
minimum?
two we need. We need two variables minimum.
To perform clustering. So what's asked here is the variables or the features, not the groups.
One,
Okay.
ma'am.
Yes, one, exactly.
One.
Yes, so when we look at groups, the groups can be more than something, but what you want is the number of features or the variables that you are trying to look at. The features can be one, it's like minimum can be one feature that you want a group to be different or clustered in between. Okay.
Okay,
Yeah.
ma'am.
So which of the following method is used for finding an optimal cluster in K-means algorithm? So we just saw it now. Oh, I guess we didn't saw it correctly. Answer says something else. Slides had something else. Uh, yes. So do you know?
I think Manhattan or Euclidean.
Yeah, it's like in the lecture slides it was Euclidean, but answer key says Manhattan. So we'll have to check it. You can also check if this question is in your today's assignment. So kindly check it before answering. Okay. Yes. So probably both of them for them should be correct. But if not, and if they're looking for one answer, Manhattan is what they are saying here. But if there's something else, you can look around it. Movie recommendation systems are an example of. So what all follows for a movie recommendation system? So well, you can classify them, you can cluster them, you can learn and check for different methods. You can do regression there.
D, ma'am. 1, 2, 3, 4.
Exactly. Again, so how can clustering that is unsupervised be used to improve the accuracy of a linear regression model that is a supervised learning? So just read the data that has been given to you and see if it makes sense. If it does, it's fine. If it does not, choose one accordingly. So creating different models for different cluster groups. Yes. Creating an input feature for cluster ID as an ordinate variable. That is why we are doing clustering analysis. Creating an input feature for cluster centroids as a continuous variable. That is also true. Creating an input feature for cluster size as a continuous variable. That is also true. So the answer would be 1, 2, 3, 4. Okay. So keep in mind, it's also for ordinate variables, it's also for continuous variables, it is also for interval data set. Okay. Yeah, so you can directly compute the values over here. You know the formula for Euclidean distance, you know the formula for Manhattan distance, what the answer would be.
3.61 and 5.
Yeah, yes. So for Euclidean, how you do is you take the difference in between the two values. So you do x2 minus x1 whole square plus y2 minus y1 whole square. So what values that you have over here? You'll have 3 minus 1 whole square plus 5 minus 2 whole square, right? So you have 2 square plus 3 square 9, so that is square root of 13. Probably the answer is 3.61 square root of 13 gives you. And another is your Manhattan distance, that is nothing but absolute of differences that you get. So your absolute difference here is 2, absolute difference here is 3. The answer would be 5 in that case, okay? Last, discriminant analysis does not require the grouping variable to be known at the beginning. Is it true? So we just saw it was which type of learning method. So clustering was one, where this was unsupervised. And this was supervised. And they say that it does not require an information to be known before beginning. So is it true or false? Come on, you know the answer for it. So if it's supervised learning, you want to know the information beforehand, right? So is the given statement true or false?
False, I think.
Exactly. So that's it for today's session. If you have any doubts, you can stay back or else we are done for today. Thanks for joining.
Ma'am, the difference between supervised and unsupervised.
You want to know?
Yes, ma'am.
Okay. Here. So basically, supervised is something when you are given some sorry, let's start from unsupervised. Unsupervised is something when you don't have any information about the data that you will have in your hand, the data that you will be doing your analysis through. Whereas supervised is beforehand you give some information to the data that you know that okay, this particular variable is linked to this data set or to this cluster, this particular variable is linked to this data set or this cluster. So there are two distinct features that will help you know that okay, this is the kind of data set it is. So let's say I'm trying to do some segmentation analysis or something. So for me, I've gotten two different, or most, I have gotten some all sorts of data sets. So I'll try and label my data set with each and every information that have been given to me. So that is a kind of supervised learning. Whereas unsupervised is you don't have any information. So what you are truly on your own. You're truly based on you're 100% relying on the technique that you are trying to build on to differentiate the data set that have been given to you. So here cluster analysis is something that is unsupervised. So here it is only based on this Euclidean distance metric or the Manhattan metric. So either Euclidean distance or your Manhattan, or the last one Minkowski that we saw. Okay, so this is like based on it. Whereas you also have another method called as discriminant analysis. That is nothing but based on when you have your data set labeled. So let's say I have a set of data, I have A and B. Now I'll directly label my data as one as A, another as B, and I'll give it to my cluster to differentiate them. Now the cluster knows that it wants to differentiate in between two different data sets, it will directly differentiate. So here it was based on the input from the user, whereas on the other hand, it was not. It was based on how your data set are within that particular cluster. So that way it would independently go around and it will make a cluster, and that cluster will eventually help you classify in between the data sets. Am I clear?
Yes, ma'am. Thank you, ma'am.
Thank you.
Ma'am, also I have a basic question that is from hypothesis testing. Okay. The question is that when we are rejecting a null hypothesis, so we are rejecting the statement we have to prove. Okay.
Yeah,
Okay,
yes.
ma'am. Thank you, ma'am.
Thank you. Okay, thanks for joining.
Okay, ma'am.